It's crazy to think that the little wisps of steam rising from your morning coffee can be used to move this massive locomotive. But a couple hundred years ago, engineers developed the technology to extract energy from fire and use that energy with water and steam to move this huge machine. In the previous video, we learned about how Thomas Newcomen invented the world's first steam engine by figuring out how to use steam to create a vacuum and move a piston in order to pump water out of a well. Throughout the late 1700s, engineers such as James Watt improved Newcomen's design, enabling it to more efficiently use a higher percentage of energy released from fire and making it run at more cycles per minute. Watt also redesigned it so that both directions of the piston's movement were used to output power and do work. Also around this time, stronger steel and improved manufacturing and machining techniques were developed. And in 1800, the first high-pressure steam engine was designed. From then on, steam engines began to find their way into steamboats, factories, and even carriages, as you can see in this image from 1828. At the same time, larger and higher pressure steam engines were designed to pull trains, and by the 1860s, this locomotive's engine design was both shrunk down to power tractors, as well as scaled up to be strong enough to pull massive trains across Europe and the United States. To understand how steam engines were able to become small and mighty enough to drive the Industrial Revolution, we're going to examine the design of a simple steam engine from the 1860s, and understand exactly how fire, water, and steam are used to create tons of force. Let's begin by exploring this traction engine, manufactured by the English company Ransom, Sims and Jeffries. It was basically an early tractor used for plowing fields, threshing wheat, powering machinery, and hauling heavy loads, and its design is essentially a smaller version of a locomotive's steam engine. Let's take apart this traction engine and look inside. Here we have a firebox for burning coal. The firebox heats up a sealed tank of water, and a set of tubes submerged in the water carry the hot fumes from the firebox to the smokestack. At the top of this tank of water is a sealed space where the water is boiled into high-pressure steam. The steam builds up and is trapped, and the only way for the steam to escape is by traveling through a slide valve, a cylinder, back through the slide valve, and then the exhaust. As the high-pressure steam follows this path, it hits the piston, which causes the piston to move, which in turn moves the piston rod. The movement of the piston rod transfers motion to the flywheel, causing it to rotate, which in turn rotates the wheels of the tractor, or whatever farm machinery may be attached. We still have high pressure on this side of the piston, but the piston has reached the end of its stroke, so it can't move any further. So the slide valve moves over and creates a new path for the steam to vent through the exhaust and into the open air. When the slide valve moves over, it also blocks the steam from applying pressure to this side of the piston, and at the same time it opens up a path for high pressure steam from the boiler, allowing it to push on the other side of the piston. Now the piston is pushed in the opposite direction, and once it reaches the end of its stroke, or movement, the slide valve shifts back over, thus completing one full cycle. Because steam is pushing on the piston in one direction and then the other, back and forth, while the opposite side is venting through the exhaust, it is called a double-acting cylinder. It is this intermittent venting of the steam that causes this familiar sound of a locomotive. This is the basic idea behind how traction and locomotive steam engines convert energy from fire into moving a wheel. But you may be thinking to yourself, a train is massive. How could this steam possibly have enough force to move an entire locomotive and dozens of cars? Well, to answer that question, let's explore the concept of high-pressure steam. Here we have a piston that moves back and forth in a cylinder, with one side connected to a tank of boiling water and steam, while the other is open to the atmosphere. As the steam molecules bounce off the metal piston, they impart a small force. The sum of the forces of all the molecules divided by the area is called pressure. This kinda seems like the Newcomen engine in the previous episode, doesn't it? However, here, the power is generated from high pressure against the atmosphere, compared to atmosphere against a vacuum with the Newcomen engine. So in this engine, if you increase the pressure, then you'll have more force on the piston to use during the power stroke. So how do we take regular steam from boiling water and turn it into high pressure steam? Prior to and throughout the Industrial Revolution, European scientists were deepening their understanding of pressure and discovered that there are essentially 3 ways to increase the pressure of a gas. The first way is to increase the number of molecules. Since each molecule imparts a little force on the piston, increasing the number of molecules increases the amount of little forces on the piston, and so, as the number of molecules goes up, the pressure increases. The second way is to increase the temperature. Temperature is an average measure of how fast the molecules are moving, rotating, and vibrating. So, as you increase the temperature, you increase the average kinetic energy of the molecules, and consequently how much force each molecule imparts when it bounces off the piston. Finally, decrease the amount of space. If molecules are closer together, they don't have to travel very far before bouncing into each other, changing direction, and hitting the piston again. The smaller the volume of a container, the more bounces the molecules apply to the walls and piston. If we put this all together, we understand that if we decrease the volume, increase the temperature, and increase the number of molecules, the pressure will rise drastically, reaching around 620 kilopascals of pressure, or 90 pounds of force per square inch for this traction engine. But what does that number even mean? Well, for this traction engine, the piston's diameter is about the size of a dinner plate. So with a pressure of 620 kilopascals, the overall force from the steam on this plate-sized piston comes out to be 2,600 kilograms of force, or almost 3 tons. That's equivalent to trying to lift the weight of about 2 cars balancing on a dinner plate, or a stack of bricks, one on top of another, 72 meters high. Now when we get to locomotives, the pressure is even higher, more than twice the pressure of the traction engine, and the diameter of the pistons are much larger, at around 71 centimeters or 28 inches. So the total force across the area of the piston in a locomotive can reach up to 53,000 kilograms, or more than 58 tons of force. That's the weight of about 40 cars placed on a diameter the size of a car's wheel. What's more is that locomotives have 2 pistons on either side, effectively doubling the force. That's a lot of force, definitely enough to move this massive train. Let's return to this image of a steam-driven carriage from almost 200 years ago. I like to think about what the people riding on top of this cutting-edge carriage were thinking. Were they imagining their society had reached the apex of human innovation? Could they have dreamed up planes or instantaneous worldwide communication? Could they have known the impact that burning coal-fired steam engines would have on the global climate? Nearly 200 years later, we know that while these inventions drove our economy and enabled access to many modern conveniences and breakthroughs, the coal and other fossil fuels burned by engines during the Industrial Revolution and up to today changed our global climate and has put us at great risk. Engineers and scientists must not only consider physics, efficiency, and design, but they must also consider sustainable sources of energy and the impact these inventions can have on our lives as well as our planet. That about wraps it up. If you haven't already watched the first video on the Newcomen steam engine, take a look. Thank you for watching. Don't forget to subscribe, like the video, leave comments with your questions and thoughts, and tell your friends and family about something you learned today.